Good morning, everyone, and welcome back to the second part of the tutorial on the mathematics of deep learning. Or good afternoon or good evening if you are still jet-lagged. My name is Giryes from Tel Aviv University, and I will talk now about several theories related to generalization error, stability, and how we may solve optimization problems in deep learning. In the first part, we heard some introduction about deep learning, the great result it achieved, and as Renee mentioned, the purpose of this tutorial is not to propose a new technique that achieves X% better performance than other techniques, but to try to explore or understand why we are capable of getting great performance or the great performance with deep learning that we are getting today. So I will be giving now two talks, one after the other. Joan, Bruna could not come here, so I will be giving two talks. The first one will be about the metric properties of deep learning, and the second one will be about the generalization error in deep learning and how we may solve optimization problems in deep learning. So just a quick overview to what has been said before. Deep learning achieves cutting-edge performance in many applications. It is used for disease diagnosis, for language translation, for video classification, for handwriting recognition, for sentiment classification, for image denoising, depth reconstruction, super resolution, and many other applications. In this talk, we will use this very simple structure to describe a neural network. This simple structure corresponds to most of the networks that we are using today. A single layer in the neural network is simply multiplication by a linear operation x, followed by a nonlinear function. And then if we take this simple building block and concatenate it together, we get a neural network. And if we concatenate lots of such building blocks, we get deep neural networks. Now, if we add a skip connection, we get a residual neural network. If we use the same building block with the same linear function in all the layers, we get a recurrent neural network. And if X is a convolution, we get convolutional neural network. So this simple structure includes most of the neural networks that we use today. So this is just a brief overview of what Renee mentioned at the first part, in case you didn't attend it. And then for the nonlinearity, there are many options to be used, but the most popular nonlinearities that are used today are the ReLU, sigmoid, and hyperbolic tangent. And today, ReLU is more commonly used than the sigmoid and the hyperbolic tangent. And another type of nonlinearity that is used in addition to this simple nonlinearities is the pooling operation that take neighboring values and take either their maximum value and then we get the max pooling, or their average value and then we get the mean pooling, or the average pooling, or it take a certain LP norm and then we get LP pooling. So this is the structure of the neural network that we will consider today, and I will try to provide some insights of why we are capable of getting great performance with neural networks. So there are many interesting questions that we would like to ask about neural networks. What is one of them? What is so special with the structure of the neural network? Another question is, what is the capability of neural networks? What we can do with them? What we cannot? We know that we can get great results, but the question is to what extent we can improve the results, or in what application we can or cannot use deep learning. Another question is, how many training samples do we need? which I think is a very important question. So for challenges such as the ImageNet or object detection, we can get, I may say, as many training examples as we want, because we can use the Amazon Mechanical Turk, and it's relatively cheap to create these large data sets. But if you want to use deep learning for medical applications, it's very expensive to get lots of training examples. And then the question is how much money you want to pay to the doctor to label all the training data. And in many cases, if you will take two doctors, they will give you two different opinions. So it's very hard to get reliable training data. So a very important question is how many training examples we need. Another question is what is the role of the activation functions? What happens to the data throughout the layers? What is the role of the depth? Why deeper networks are better than shallower ones? And what is the role of pooling? So in this part of the tutorial, we will try to answer part of these questions. Part of them were addressed at the first part by Renee, and I will try to address the other ones. So the outline of this part, we will see first that if we look at the neural network with random Gaussian weights, the Gaussian mean weights of the data is a good measure for the complexity of the data. And one of my important take-home message for you today is that many researchers today, when they try to analyze deep neural networks, they try to analyze just the network itself or just the network architecture. And I believe that if you want to understand the behavior of neural networks or of deep learning, it is not sufficient just to look at the network architecture, but you should look jointly both at the network architecture and at the data that you are processing. So when you want to answer the previous questions, you must take into account not only the depth of the network or the size of the network, but also the complexity of the data that you are processing. So I think that both the complexity of the data and the complexity of the network should be studied together and not in a separate way. So the first thing that I will talk about is that, or mention, is that if I'm talking about complexity of the data, so we want to have a measure for the complexity of the data, and the measure that I will be using is the Gaussian mean weights. The second point that I will try to pass in this tutorial is that deep neural network keep the important information of the data. If you are putting a data in a neural network, at the feature space, at the output of the network, most of the information will be still available for you. Yet, if you want to do classification, you don't care about keeping only the information. You want to do also, you want the network also to distort the distances in the data to make it more easy for classification. And then we will see that if we take a neural network with random Gaussian weights, such a network will give you features that are good for the average points in the data. And then one of the important things that you will get with training is the separation of the boundary points in the data. And we will see what is the meaning of the boundary points. After we'll see these things, we will move to talk about generalization error in this second talk. We'll talk about generalization error in neural network, what we can say about generalization error, because many times we get very good training error, but in the 80s and 90s, one of the main problems in neural networks was overfitting, and today we get very good generalization. The question is what we can say about the generalization error in neural network. And then we, at the end, if time permits, we'll see how we may solve optimization problems with neural networks. So in each part of my talk, I will have certain assumptions on the network. These assumptions will change through the talk. And at the beginning, I will have more restricting assumptions on the network structure. And then as we will go through the talk, I will have less, restricting assumption on the network. But at the beginning, we will study a neural network with random Gaussian weights. We'll just assume that we have a feed-forward neural network with random Gaussian weights at the linear parts. And the reason we will do that is that because infusion of random Gaussian weights reveal the internal properties of many architectures, and the same happened in compressed sensing, in fast retrieval, in sparse recovery, and also in several works in deep learning. So in many cases, if you want to understand or reveal some certain underlying properties of a system, if you study the system with random Gaussian weights, you will get some of the internal properties of the system. The second assumption is that we will ignore at this part the pooling. And the reason for that is that in recent works, it was shown that pooling provides shift invariance. So we will just assume that someone aligned the data in a nice way for us. And we will assume that we just have the ReLU or a general nonlinearity. And this will help us to reveal the properties of the other components of the neural networks other than the pooling. So some work show us that pooling gives us some shift invariance. So we will ignore at this part of the talk pooling. We will return it later. And this will help us to reveal the role of some of the components in the neural network. And the last assumption I will assume in the first part of the talk is that the data that we are processing belong to a certain low-dimensional set. And this assumption is the easiest to justify because we know today that all the data that we are processing belong to a certain low-dimensional set, such as Gaussian mixture model, or whether we are, or sometimes we have signals with sparse representation, or we have low-rank matrices, or we have general low-dimensional manifolds. So we'll assume that the data belong to a certain low-dimensional manifold, or to a Gaussian mixture model, or to a certain low-dimensional set. So when I talk about low-dimensional set, the question is how we measure the complexity of this set. The question is whether we stick to one of these models, to Gaussian mixture model, or to sparsity, or to low rank, or whether we can have a general measure that tells us what is the complexity of the set that we are processing. So the measure that we will be using is Gaussian mean width, and I will try to convince you that Gaussian mean width is a good measure for the complexity of the data. For that, let's take the following example, and let's assume that we have sparsely represented data with sparsity 1, and we are looking at the space of R3. So if we have sparsity 1 and we are in R3, basically the data lie on one of the general axes. Now, in this case, the data is sparse with sparsity 1, and very simple. And if we will multiply our data with a certain linear operation x, the data will be still sparsely representable, but with rotated axes. So we are still in the sparsity model. Yet, if we will apply a certain nonlinearity, such as the ReLU, the data will stop being sparsely represented. It will be still low-dimensional, but it will not belong anymore to the sparse representation model. Therefore, if we have a certain assumption on the model at the input, we cannot assume that this model remains with us throughout the layers. Instead of sticking to a certain model, we will use the Gaussian mean width, which is a measure for the complexity of the data. So the Gaussian mean width of a set upsilon is the expectation of the supermum of the difference between 2 points in the data, and the inner product of this difference with a random Gaussian vector. And the expectation is over the random Gaussian vector. Now, to make this definition simpler, let's forget for a moment the expectation part, and let's focus only at the inner product between the difference between V and W and the random Gaussian vector G. If we will look at this set, upsilon, the supermom between the difference between V and W that belong to this set and the random Gaussian vector G is basically the width of this set in the direction of G. So basically, the supermom of this inner product is the width of this set in the direction of G. What the expectation term gives us is the average over many vectors G that goes in different directions. So basically, the Gaussian mean width is the average width that we get if we take the inner product with a random Gaussian vector. And this average width gives us a measure for how complex is this data. Now, why this property is interesting? The reason that this property is interesting and desirable to be used is that the square of the Gaussian mean width is a measure for the dimensionality of the data. And we'll take several examples. If our set is a Gaussian mixture model with k Gaussians, then the square of the Gaussian mean width is the order of the number of Gaussians. And for you that are familiar with Gaussian mixture model, you will notice that the number of Gaussians is a good measure to characterize a Gaussian mixture model. If we are looking at data with sparse representation with sparsity k, the square of the Gaussian mean width will be order of the sparsity times log the ambient dimension of the data. And again, if you are familiar with sparse representations, order of the sparsity times log the dimension of the data is a standard measure for the complexity of sparse representation. And the same hold if we will look at this square of the Gaussian mean width of low rank matrices and other manifolds. So what we get here is that we have a measure that gives us the complexity, a number for the complexity of the data, and this measure is good for different low-dimensional models. Now, why this measure is useful with deep learning? So a theorem that we proved says the following. If we have a data upsilon that goes through one layer of a neural network, if the square of the Gaussian mean width divided by the number of features at the output is small, then we will get that the Gaussian mean width at the input approximately equal to the Gaussian mean width at the output. Which means that if we had small Gaussian mean widths at the input of one layer in the network, we will have a small Gaussian mean widths at the output of this layer. And therefore, this theorem provides us with two important properties. The first thing, it tells us that if we have data that is low dimensional, the features in the network will remain low dimensional. The second thing is that because this property holds for each layer of the network, we can prove things just focusing on one layer on the network, and then we will get results for the network as a whole. Because if our theorems will rely just on the fact that we have data with small Gaussian mean widths at the input of one layer, and then we know that the Gaussian mean widths remain small throughout all the network, our theorem will apply to all the layers in the network. Now, with this understanding, we will try to study the stability of the layers of the deep network. And using the property of the Gaussian mean widths, studying the stability at each layer will give us a result on the stability throughout the whole network. So the assumption for studying the stability will be the following. We'll assume that the input data lie on a sphere. And this is practice that is used in many neural networks when a practitioner normalize the input data. The second assumption is that, as I mentioned, that the weights in the network are random, with random Gaussian weights. And we will assume that the nonlinearity is an element-wise activation function, which can be either the ReLU or the hyperbolic tangent or the sigmoid. And the last assumption is that the number of features at the output of the layer scales as the square of the Gaussian mean widths times delta to the power of -6, where I will explain what is delta in a minute. The second theorem that we have with this assumption is that each layer of the network is a delta isometry in the Gromov-Hausdorff sense between the sphere and the Hamming cube. Now, what does this mean? This theorem claims that if we look at each layer and if we look at the rows of each linear operation in the network, these rows, each of them, create a separation by a hyperplane of the space. This mixture of hyperplanes create a tesselonation of the space, which stands in line with the result of Montufar from 2014. And then we have that if 2 points lie on the same on the same tile in the tessellation, it means that these 2 points at the input were very close to each other. So this result claimed that each layer of the network creates a tessellation of the space, which means that we have lots of tiles. And then if we have 2 points that belong to the same tile at the output, these 2 points were very close at the input. The significance of this result is that each layer of the network keeps the main information of the data because it keeps local distances. And another important conclusion from this result is that the network can be used for hashing. And this was done by the work of Romaneska in 2016, which showed that it is possible to use these properties of the network to have good hashing with neural networks. And also, Maskey and Bly at 2012 and 2015 showed that it is possible to train a neural network that will give you a local sensitive hashing. Now, now if we have local preservation of the distances in the network, as I mentioned before, it means that we keep the important information of the data. If we keep the important information in the data, it means that we can also recover the input of the network from its output. And for that, we have the following theorem that claims that there exists an algorithm that can recover the input of a layer in the network from the output with an error that scales as delta to the power of 3. Now, this result holds just for one layer. So if we will have k layers, it means that after k layers, the reconstruction error will be of the order of k to the power of delta, k times delta to the power of 3. And this stands in line with the result of Mahendran and Vidaldi from 2015 that showed that it's possible to invert a network, which means it's possible to recover the input of a network from its output, and that the distortion in their construction is linear as you go deeper in the network. And here you can see the results that they got. You can see that if you try to recover the input from just the first layer, you get this result. And as you get deeper in the network, you get larger distortion. But this distortion, as you can see, is mild and not very strong, as predicted by our theorem that claims that the distortion that you get in the reconstruction is linear with the depth of the network. Now, as I mentioned before, the fact that we can recover the input of a network from its output is not a sufficient thing if we want to use the network for tasks such as classification. Because if the only thing that we want to do is to recover the input from the output, we can just keep the information as is. So next, we want to try to understand what happened to the distances between points in the data. And for that, we will use the following assumptions. We will assume that the input data lie on is general, lie in a general low-dimensional subspace. Again, we will assume that we have random Gaussian weights. But here, we will assume to analyze what happened to the distances and not just to have a result that is correct with respect to keeping the information. We will assume that the nonlinearity that we have is the ReLU. Now, I think that this is a very mild assumption because we know today that one of the strongest, that ReLU is the most popular nonlinearity that is used in most networks. And the assumption, the last assumption that we'll have is that the number of features at the output of each layer is of the order of the Gaussian mean widths to the power of 4. We believe that the fact that we got that the number of features should be as the size of the Gaussian mean widths to the power of 4 is something that just follows from our proof technique, and that we believe that it's possible to improve this factor to be to the power of 2. So what we showed that if you take 2 points at the output of one layer of the network, if you take point V and look at its output psi Vx, and take another point W and look at the output of this point and measure the distance between these 2 points, and then compare this distance to the distance at the input of this layer, you will find out that this distance changed, is distorted with a factor that depends on the angle between these 2 points. So if the points V and W has small angle between them, then the distance at the output between these 2 points compared to the distance at the input will be, the distance at the output will be smaller by a factor of 2 compared to the distance at the input, which means that you get shrinkage of the distances if you have small angles between 2 points. On the other hand, if the angle between the 2 points that you're looking at will be very large, you will get that the shrinkage of the distances between these 2 points will be only by a factor of 0.75, which means that each layer of the network distort the distances between the points in the data at the input based on the angles between these 2 points. If the angles are very small, you will get strong shrinkage in the distances. If the angles are very large, you will get weaker shrinkage in the distances, which means that the network is distorting the data based on the angles between the points. And this is very useful because we know that in many classical computer vision applications, people observed that angles between points are more meaningful for classification than the Euclidean distances. So what the network is doing here, it's distorting the distances, the Euclidean distances between points, such that the Euclidean distances will resemble more the angular distances than the original Euclidean distances. Now, this result is true for one layer. And therefore, it is important to ask what happened to the angles throughout the networks. So if I tell you that the Euclidean distances in the network shrink based on the angles, I should tell you also what happened to the angles when you go deeper in the network. So it is possible to show that if you look at the distance between the angle at the output of one layer and the angle between these 2 points at the input, you will see that the angles remain almost the same throughout all the layers. So if you look at this graph, in this graph you have the angle at the input of one layer and the angle at the output of this layer. And then you have the relationship between the angle at the input and the angle at the output in the blue line. Now, if you will look at this blue line, you will observe that if the angle between these 2 points was larger than pi divided by 2, or larger than 180 degrees, the angle will become 180 degrees approximately, and this is because we are using the ReLU, and the ReLU is just projecting things to the positive orthant. So it is clear that it is not possible to have angle which is larger than 180 degrees because we are just projecting everything. It's not possible to have angle that is larger than 90 degrees because we are just projecting everything to the positive orthant. And therefore, the interesting location is the angles between 0 and 90 degrees. So if you look at what happens to the angles between 0 and 90 degrees, and you will look at the blue graph, you will see that the behavior of this graph is linear. The shrinkage is linear. And if you have a small angle, then the output angle will be almost the same up to a factor of 0.95. And if the angle is between 45 and 90 degrees, the output angle will be shrunk by just a factor of 0.8. And this is, and we tested, so this is what is predicted by our theory. We tested it also empirically, and we get the same behavior also empirically. So basically, what you have is that angles remain almost the same throughout the layers of the network. And the more important thing is that the order between the angles remains. So if you had 2 points that were with small angle between them at the input, the angle between them will remain smaller than other 2 points that had bigger angle at the output. So if we will try to illustrate what our theorem predicts, let's consider this simple example. Let's assume that we have these 3 points, and we have this magneta point in class 1, and this orange and green points in class 2. And you can see that the angle between these 2 points is smaller than these 2 points through the Euclidean distance between them is quite the same. So our theorem predicts that if you will look at the output of one layer in the network, you will get that the distances between the points that belong to the same class are smaller than the distances between points that belong to different classes. So this is what's predicted by our theorem, but I have cheated here a bit. So our theorem predicts this thing, but I cheated here in 2 things. First thing is that, which is the most obvious, is that in real data, the angles will not be always as nice as we have them here. Many times, we may have small angles between points that are from different classes and large angles between points from the same class. When you look at a network with random Gaussian weights, this network is blind to the different classes, and therefore for this network, if you have 2 points that have smaller angle between them, it will consider them as they are from the same class. Though this will not be the case in reality. And therefore, we are not using networks with random Gaussian weights. The second thing is that in these examples, I selected the origin of axis to be here. If I will select the axis origin to be in another place, I can set the angle between these 2 points to be smaller than the angle between these 2 points. So if the axis origin will be here, then the angle between these 2 points will be 0, and then the angle between these 2 points will be very, very large. Now, this understanding may give us a hint of what training gives us. And this can be seen also from the proof technique that can be found in our paper. If you think about it, as I now mentioned in the problem of selecting the axis origin, the axis origin set exactly the angles between different points. So if you are just using a network with random Gaussian weights and no bias, which I ignored at the moment, the axis origin is set to 0, and then you are just looking, you are lucky if the angles are smaller, and you are unlucky if the angles get larger than what you want. But if you are using training, then you can train the network to set the axis origin in the place that you want, and then in this way you can cause the network to shrink distances between points that belong to the same class more than the distances between points that belong to different classes. And from the analysis that we did for random Gaussian weights, we believe that this is one of the things that the network is doing. And I will illustrate this in several empirical examples. So, before I move to looking at what training is doing, I will just mention what conclusion we can get from this result of random Gaussian weights. So this result that we got from random Gaussian weights mean 2 things. The first is that the distortion in the network of the Euclidean distances is based on the angle between the points, which means that if we can put the axis origin in the way that we want, in the place that we want to put it, we will be able to distort the distances in a way that will cause the data to be in a better shape for us. The second thing is, if you will look at the shrinkage of the distances, if you look at this graph that shows us the shrinkage of the distances at the output of a layer compared to the distance at the input as a function of the angle, you will see that the shrinkage of the distances is bounded between half and 0.75. This means that, so this results in a similar way to the result that I showed at the beginning with the Gromov-Hausdorff stability, claims that our network is stable with respect to the distances. So distances cannot change too much. So if distances cannot change too much, they can shrink either by a factor of factor of half or by a factor of 0.75. It means that most of the points, most of the local distances remain the same. So if we may have a good network for an epsilon net of the input, and we will have good training error for this epsilon net, we will have a good error at the output. So if we will use Sudagov minoration, the number of data points that we will need in the training will be the exponent of the square of the Gaussian mean widths. So of course, you don't want to have such a bound for the number of training examples that you need. And in the second part of my talk, I will talk about better generalization error bounds than this one. But the reason that I present this bound is because this bound tells us that the number of training examples that you need depends on the complexity of the data. If you have more complex data, you will have more number of training examples. If you have less complex data, you will need less number of training examples. And of course, a better analysis should be done to have tighter bound that will give you a better proxy for the number of training examples that you need. Now, till now, I presented an analysis of networks with random Gaussian weights. Now, what I will try to claim now is that this analysis is good for the average points in the data, and one of the main goals that we achieve via training is classification of the boundary points. And for this, we did the following experiments. We looked at 3 different data sets. We looked at the MNIST, CIFAR10, and the ImageNet data set. And for the ImageNet, we looked at the VGG16 network. And we computed the inter and intra-class distances. For the sake of time, I will present just the ImageNet results. So we did the following example. We looked at the interboundary points distance ratio. What does this interboundary points distance ratio mean? Take a point, random point V, and then take the point W, which belongs to another class and is the closest one to V from all the other classes. So you are looking for the closest point to V from another class. So this will be the point that will harm us the most in the classification task for the point V. And then look at compute the distance between V and W, and then look at the output of the point V by the network, and then look at the closest point to the output V at the output of the network from another class, and this output is not necessarily the output of W. And then we compute the distance between this output and the output of the point V, and compute this distance ratio. We call this ratio the interboundary distance ratio. We repeat the same thing for intraboundary distance ratio, which means take a point V, look at the farthest point W that belongs to the same class. Now compute the distance. Now look at the output of this point V and look for the farthest point from this class that belong to the same class. Again, this output is not necessarily the output of the point W. Compute the distance between them and compute the ratio. And we call this the intraboundary point distance ratio. And then we plot a histogram of the interclass distances and the intraclass distances for a random network and for a trained network. Now, this plot or this histogram, I believe, will not surprise anyone here. And clearly, if we will look at the histogram of the trained network, you will see that distances of points from the same class, from different classes, become larger, and distances of points from the same class become closer to each other. But if we will look at the ratios of the output and the input of the random network, the ratios are the same for the interclass distances and the intra-class distances. And the reason for that is that, as I mentioned before, a network with random weights is blind to the different classes, and therefore, in many cases, we will have points from the same class with smaller distance, from different classes that will have smaller distance than points from different classes, from the same class. Now, this result will not surprise anyone. But then we repeat the experiment and look at the average points distance ratio, which means take 3 points at random, V, W, and Z. V and W belong to the same class. Z belong to a different class. Calculate the difference between V and W that belong to the same class and between V and Z that belong to different classes. And then look at the output of V and W and the output of Z and calculate the ratio between the distance of V and W at their output and their input, and the ratio between the distance between V and Z at the output and the distance between V and Z at the input. So we compute these ratios, and surprisingly, we get that the histograms of these just random points that we picked for the trained network looks the same if we look at the interclass case and the intraclass case. And they are very similar to the random network. So notice that when we looked just at boundary points, we got the result that we would expect, that points that belong to the same class get closer to each other in trained network, and points that belong to different classes get farther from each other. But when we just pick random points, we get that the distances are very similar to the random network. So the conclusion from that, or our conclusion from that, maybe you have a different opinion on that, is that on average, distances are preserved in the trained and random networks, which is what we have seen in our theorems. And therefore, the fact that we analyze the network for just random Gaussian weights is not something that we did for Vane, but something that holds for most of the points also for trained network. Yet, the main difference between the network with random Gaussian weights, which is the standard initialization that is used today, and the trained network is with respect to the boundary points. The interdistances become larger, and the intradistances shrink. So one of the conclusions from that is that we may view deep neural network as metric learning, and then it is possible, and I will skip this part, it is possible to propose different objectives for neural networks that rely on the metric between the angles and the metric between the distances. And if you use this metric-based training, you can get better results than networks that just train with the sigmoid, with the softmax, or without usage of the metric of the network. And this is the example of results that was achieved by Huang, Q, Sapiro, and Calderbank that trained using metric learning, and they got better results on MNIST with small number of training examples and better results on faces in the wild. So this ends the first part of my talk. And now I will move to the second part of my talk that will talk about generalization error and how we may solve optimization problems with deep learning. If someone has questions, he may ask now, or we can leave all the questions to the end. Yeah. Can you go to the mic?
Can you give some intuition on the surprising result that you showed where the distance matrix remained the same for the ratios that you were taking? The two normal Gaussian curves remain pretty much the same.
So our intuition is that our assumption that the angle is the thing that should discern between different points is true for most points in the data. And then the most problematic thing is the points at the boundary that don't have these good angles. And therefore, what training is doing is that it is correcting the random network with respect to these errors to where to put the angles. So as I showed in the as I showed in this example, our theory predicts that you get distortion based on the angles. Now, for most points, if you will throw the axis origin in random places, you will get small angles between points in the from the same class and large angle from different classes. Now, there are some boundary points that you should pick for them the axis origin. So therefore, for most of the points, you get the same behavior, and for some points you get the difference behavior. Yeah.
So I kind of have two questions, but maybe I'll start with just asking one, which is, you mentioned earlier that like angles are kind of what's important instead of distances, and I guess that's true at the final layer too, where you're doing classification, because what you really care is if your representation is aligned with the corresponding vector for that class. So I was wondering why you are doing this analysis in terms of the distances instead of the angles.
Because at standard networks, what you use at the end is softmax or SVM. And then when you use this, so you use a linear separation, which is more based on the Euclidean distances than on the angular distances. So basically, you are preparing the features to be more linearly separable. And when you use these linear separations, the Euclidean distances are more important.
I don't think so, actually. Like, well, I'm talking about the penultimate hidden layer, like before the softmax, right? So at that layer, what matters is like whether or not your angle is aligned with the angle of the corresponding output vector, right? Or
so you can view it in two ways. So if you have very large angles, it's good. And on the other hand, if you have very large distances between different classes and small distances between the same class, it's also good. So you can analyze either that or the other one.
But like, let's say we just had like, I don't know, two classes, and you can have 2 points which are very, very far apart, but are like perfectly parallel, and perfectly parallel with the corresponding output vector. And the distance there doesn't really matter. I mean, modulo the biases of the network, right? Because they're both going to have maximal inner product for a given norm with the corresponding output.
So, yeah, so if you have just 2 points, so it's right. But if you have many points, so it's a desirable thing is that this many points will shrink towards themselves and will be farther from each other. So at a certain point, at the second part of the talk, I will mention why we think that these distances are important, and we will see that one of the factors that affect the generalization error is the distance that you have between the points and the separation line. So I will get to that.
Okay.
Your picture with how the random matrix applied to a set looks like a subdivision of tessellation of space by hyperplanes. So if we have a sequence of matrices, we have sequences of such tessellations. It looks like a technique like random forests with tessellation of the space by hyperplanes and hierarchical subdivision of them. If this relation really exists, if it is studied, and if your reasoning about this distance scaling is applied also to random forests.
Okay, so the relationship between deep learning and random forest I am aware of, There is a work by Richard Baranuk that he shows that deep neural networks can be viewed as generated from a certain Bayesian framework. And there he showed that both random forest and deep learning can be generated from the same framework. So I will just take the last questions. I'm sorry for, because I want to have enough time for the other second part, and then at the end we'll have more time for questions.
It's a very quick one. So I think one of the graph shows that you always shrink distances at every layer. However, having processes by 150 layers, your experimental graph showed that your average distance is preserved. So there seems to be some discrepancy.
So it's a matter of normalization. We just normalize the average to be 1. So shrinking or expanding is something that is relative.
Okay. So you have L2, L1 normalization somewhere.
So we just normalized all the things to be to.
And did you look what happens to the angles actually empirically? I mean, do typical angles change in any way, or distribution of angles?
So we looked at the angles from random weights and not from the trained one. And when we looked at the angles at the random weights, we get the same behavior like our theorem predicts. Okay. So I will move now to the second part. I am sorry that I couldn't pick all the questions, but at the end we will have more time for questions. The second part of the talk will be about generalization error. And if time will permit, I will talk also about solving optimization problems. And in this part of the talk, we will assume a general structure of a neural network. The only constraint that we will have is that we will assume just 2 classes, but it's possible to extend our analysis to several classes. But for simplicity, we will assume just having 2 classes. And we will assume general nonlinearity, which can be ReLU, pooling, or whatever you want. And at the output, we will assume that we have a softmax or a linear classifier. And for this part of the talk, I want you to have this view of a neural network. In a neural network, we have the input space and the feature space, which is the layer between the softmax. And let's assume that we have these 2 classes, the blue class and the red class. And we want to separate between the blue class and the red class. Now, when we take a neural network and we take the data, and this data passed throughout the layers, hopefully what we would expect to have if we are using softmax or linear classifier is to have that at the output, the data points will be placed in a position such that it is possible to separate them with a linear classifier. So if we look at the feature space and at the separating line or separating hyperplane at the feature space, which is created by either the softmax or the linear classifier, this separation line or separating hyperplane correspond to nonlinear separating line or separating border at the input space. So if you have this separating line correspond to, which is linear, correspond to nonlinear separation of the space at the input. And then and then what neural network is doing, it trains both the separating line and the layers of the network such as the line will be the best to separate the features created by the network. And as Renee mentioned in the first part, one of the things that people mention as the strong things, that's why neural networks are so strong, is that in neural networks we create both the features and the separating line at the same time compared to previous techniques where we had handcrafted features and then we trained the SVM or linear classifier or something with the kernel. Now, so this is the picture that I want you to have in this part of the talk. And I would just mention the classifiers types that we will use. So I mentioned that at the output we have a softmax or linear classifier. So if we have the output of the neural networks and denoted by Z, so a linear classifier just means that we take the Z multiplied by a linear vector W and then compare it whether it's bigger than B, a certain constant B, then it means that we belong to class 1. If it's smaller, we belong to class 2. And the softmax classifier predicts the probabilities of class I by taking the exponent of the ith value in Z and divided it by the sum of the other exponents. And the formula that we have here is for 2 classes, and it's easy to extend it to several classes. So softmax, in the case of 2 classes, also give us linear separation, but and it gives us, in some sense, the probability of belonging. It gives us probability distribution regarding the output. Now, the standard objectives that are used for training when you want to train a neural network. So if we will denote the output of the deep neural network by Z, and we denote by Ti the expected output of Zi, or the label of Zi. So a very common training loss is the categorical cross entropy, or the softmax loss, which is basically the sum of the log of Zi times Ti. Another loss, which is popular with because of SVM, is the hinge loss, which is the maximum between 0 and 1 minus Zi times Ti. And for both losses, there are many regularization techniques that are used. One of the popular ones, or previously popular one that was used, is the weight decay, which is basically penalty on the weight matrices. So you take the sum of the weight matrices, sum of the norms of the weight matrices, and this is the weight decay. Now, in this part of the talk, I want to focus on the generalization error. When you train a network using one of the losses that I mentioned before, you reduce the classification error L training on the training data. And through you may get great error. In practice, what you are interested is the error that you get on the test data or on the real data and not on the training data. And therefore, an important property of many classifiers, and deep neural networks as one of them, is the generalization error of the neural networks, which is the difference between the error you get on the training data and the error that you get on the test data. And if I will use more formal terms, the generalization error is the difference between the expected loss and the empirical loss. The empirical loss is the loss that you get on the training, and the expected loss is the loss that you get on the test. And therefore, it is very important to understand the generalization error of deep neural network. One of the early bounds that studies the error of neural network is the result by Baron from the 94 that showed that the estimation error, the total error that you get, the expected error that you get in the neural network, scales in the following way. It scales as the order. If you want to approximate a function f that is smooth with a certain smoothness CF, then you will get that your error, your total error, is decomposed of these two terms. The first term is the training error term. The second term is the generalization error term. And it is important to understand both of them. So with respect to the training error term, Baron showed that the training error term scales as the smoothness of the function divided by the number of neurons, which means that the more neurons you have, the larger the network you are using, the smaller the training error that you can get, which is quite clear, because then you can overfit the data. On the other hand, the generalization error, which is the difference between the total error and the training error, scales as the number of neurons times the input dimensions divided by the number of training examples times log the training examples. Now, this result tell us that, now notice that for the approximation error of the training data, you get smaller approximation error of the training data when you have more neurons. On the other hand, when you have more neurons, the generalization error increases. So you have a trade-off between the two. But the generalization error reduces when you have more training examples. So the more training examples you have, the better generalization error you get. And it's important to understand both of these terms. And the reason for that is that always you can have a classifier that will give you 0 generalization error. The simplest classifier that you can use is one nearest neighbor, and one nearest neighbor give you a 0 classification error on the training data, because each data will get its label. On the other hand, you can always get 0 generalization error. If you will take a random classifier will get the same error on the training data and on the test data. But random classifier is not something that you want to use. You want to analyze it, as I showed before, but it's not something that you want to use in practice. So therefore, it's important to understand both the training error and the generalization error. I will focus now only at the generalization error, but when I will talk about generalization error, always keep in mind that you want also good training error. Because in some part of the bounds, you will look at the bound and say, oh, okay, so we can use this bound to get 0 generalization error, but it's not always useful if you forget the training error. Now, there are many regularization techniques that were developed to get better regularization, to get better generalization error, to prohibit overfitting. So one of the earliest regularization terms is the weight decay that penalize the weights in the deep neural network. Another very popular regularization technique is the dropout, that randomly drop units along with their connections from the neural network during training. Drop connect is another regularization technique, which is extension of dropout. And more recently, batch normalization was proposed that is basically trying to whiten the data. And by whitening the data, if you have whitened data, it is easier to process. And when you have whitened data, the training data and the test data looks more similar, and therefore batch normalization leads both to better convergence and also to better generalization. As René mentioned at the introduction, when you train a neural network, you use usually stochastic gradient descent with backpropagation. And the reason that people are using stochastic gradient descent, or were using stochastic gradient descent initially, was because of computational demands. So when you have millions of training examples, so it's very hard to calculate the gradient of all the examples together and take gradient step using all the test data, training data that you have all together. And therefore, people use the compromise, which is the stochastic gradient descent, where they calculate the gradient using one example at a time, or using stochastic gradient descent with unit patches with several examples at a time. Interestingly, Hardrecht and Zinger in 2016 showed that stochastic gradient descent is not something that is desirable only computationally, but it's also good for generalization. They showed that using stochastic gradient descent, if you are in the proper place in the error surface, you get better generalization error. So basically, you want to use stochastic gradient descent not only because you don't have enough computational power, but also because you want to get better generalization error. Neishabur et al. At 2015 proposed a path stochastic gradient descent, where he noticed that if you look at a network with ReLU, you can scale the weights in the network in a way that you will get two networks, one with scaled weights and the other one with balanced weights, and these two networks will give you the same output. Yet if you will calculate the gradient with the network that has the scaled weights, you will get bias to the branches in the network that has higher weights, and therefore the convergence will be worse than a network with the balanced weights. And he proposed the path SGD that gets also both better convergence and better generalization error. And there are many other regularization techniques. I will go now on a sample of generalization bounds, and then I will mention one that we recently developed. So a series of works starting from 98 by Bartlett showed that the VC dimension of a network with ReLUs is of the order of the depth of the network K times the number of parameters. And therefore, with this bound on the VC dimension, they show that the generalization error scales as the order of the number of parameters that you have in the networks times the depth times log L divided by L. So we have here a very similar term to the one that we saw by Baron. And this bound claimed that, and very recently, Bartlett showed that this bound on the VC dimension, that the VC dimension of a network is bounded by the depth times the number of parameters, is a tight bound. Another series of works bounded the generalization error using the capacity of the network. Again, Bartlett showed that in 98, showed that the capacity or the norms of the weights in the network is sometimes more important than the number of neurons that you have. And this was followed up more recently by Neishabur in 2015, that showed that if you look at the norm in each, so in the result that depends on the VC dimension, you can see that the generalization error scales as the number of parameters in the network. But today we know that we may have many, lots of parameters and sometimes more than number of training examples, and yet we get good generalization. So to address that, Neishabur showed this bound that show that generalization error scales as 1 divided by the square root of L, which is the number of training examples, times the products of the Frobenius norms of the weights in the network. So you can see that this bound is independent of the number of parameters that you have in the networks, given that each layer, given that the weights at each layer has bounded norm. Yet, this bound has a factor of 2 to the power of k, which is the depth of the network. Now, if you are using relatively shallow networks, so this 2 to the power of k is not a big problem. But if you are using very deep networks, like the ResNets. So you will get here 2 to the power of 100. And we know that the ResNet generalize with much less number of training examples than the number of atoms in the universe. So notice that both the divisity dimension base bound and that the Rademacher complexity base bound scales as the number of parameters or the exponent in the depth. Okay, I'm missing here a slide, so I mention it verbally. Very recently, Sami Bengio and Ben Recht showed that if you want, in a paper called Rethinking Generalization, revisited the bounds that we have here. Now, if you will notice, you will see that these bounds that we have here take into account only the structure of the network and doesn't take into account the structure of the data. They made the following experiment. They took lots of data sets, standard data sets like CIFAR-10, and tested the performance of different networks with different regularization techniques, and checked the training error and the test error that you get for these networks. Then they took the same data, but with random labels, and applied the same networks with the same regularization techniques. Interestingly, what they got is that if you just look at the training error of the data with the random labels was almost the same as the training error of the data with the true labels. But of course, when you just have random labels, the networks cannot generalize on such data because it's just random data with no meaning. Which means that if you want to understand generalization, you cannot use techniques that are agnostic to the data, like the VZ dimension or the Rademacher complexity. But you must take into account also the structure of the data. And this was followed up by a more recent work by Yoshua Bengio and others that showed other experiments that showed that the structure of the data is very meaningful for the training of the networks. And if you have network with structure, even in the training part, you get better convergence than networks without structure. So when you want to analyze networks, the properties of networks, I believe that you must take into account the structure of the data. So we have this bound that take into account the structure of the data. We believe that it's possible to further improve it. And we show that the generalization error scales as 1 over divided by square root L, which is the number of training examples, as in the previous bounds, times the square root of the covering number with covering balls of size gamma divided by 2 of the data that you are working with. And the covering number with the diameter gamma is basically how many balls with radius gamma you need to cover the set Y. And gamma in our bound is the input margin of the data. So what is the input margin? If you remember at the first figure that I showed you, if you take a network and train it, and then you get a separation line at the output, and then you look at the corresponding separation line at the input, the distance between the points at the input and this decision boundary is called the input margin. And our analysis rely on the robustness framework from Xu and Manor from 2012. Now, the problem with the input margin is that we took a hard problem of training a neural network, and now we tell you that the generalization error of training this network scales as the square root of the covering number with balls of size of the input margin. So it means that the larger these balls are, the less balls you need, and therefore you have smaller covering, and therefore you have smaller generalization error. So basically what this theorem claims is that you need to have larger input margin. So basically you need to train a network with larger input margin. But having large input margin is a hard problem, which is hard as training the network itself. And from the first talk of René, we understood that it's very hard to train neural networks. Sometimes, so we have guarantees if we have zeros to get the global optimum, but in many cases, it's very hard to train the network, and now we are making it even more complicated. So to bypass this problem, our strategy is to give a lower bound on the input margin. So we proved that the input margin of a neural network is lower bounded by the output margin divided by certain properties of the network. So let's look at this lower bound and what we can learn from it. So first of all, we get that the input margin is greater or equal than the output margin divided by certain properties in all the bounds. And the output margin is something which is very easy to maximize. We can do it by a simple SVM problem. And it's minimized by many cost functions, such as or maximized by very many cost functions, such as the hinge loss. So with these lower bounds, we replace the input margin by the output margin, which is very easy. Now we need to look at the denominator, which we also want. We want to minimize now the denominator in order to maximize the input margin. So we have three lower bounds. We will look now at the weakest one. In the weakest ones, we show the weakest one is the output margin divided by the product of the Frobenius norms. And basically what it means that bounding the weights increase the input margin. And this is exactly what is done in weight decay, with the difference that in weight decay we have the sum of the weights, and here we claim that we need to have the product of the weights, and we have the same term of the product of the weights also in the work of Neishabur, and also in the work that René Vidal mentioned. So notice that from different perspective, we get the conclusion that if you want to use weight decay, instead of using the sum of the weights, you should use the product of the weights. But our bound, but we have tighter bounds than just weight decay, which we know that is not as good as we want it to be. So instead of the product of the Frobenius norms, we have the product here of the spectral norms, which is related to batch normalization and weight normalization. And we have a tighter bound, which is related to the Jacobian of the network. So we show that the input margin is lower bounded by the output margin divided by the norm of the Jacobian of the network. Now, if you will think about it, if we want to minimize the Jacobian, it basically means that we want to have a network with smooth decision boundaries, which makes sense because we know that if we have smooth decision boundaries, this will give us better generalization error from intuition. So here our intuition meets the theory. So the Jacobian of the network is something that is easy to calculate if you use ReLU or max pooling, because in this case, the Jacobian become a piecewise constant. And this leads also to new regularization technique, which is basically a regularization training a neural network with a penalty based on the Jacobian of the network instead of the weight or instead of the weight decay. And we tested that on several data sets. Here I present the results on the MNIST. In the paper, we have results also for many other data sets, such as the ImageNet and CIFAR 100 and the other data sets. And in all of them, we observed that as our theory predicts, using regularization based on the Jacobian is better than using regularization based on the weight decay, and it's possible to combine the regularization based on the Jacobian together with other regularization techniques such as batch normalization. Now, we extended our theory also to study the relationship between invariance in the data and invariance in the network. And we proposed also a new strategy to enforce invariance in the network. The theory that we proved, we showed that if you have a network which is invariant to T transformations, and you have a network which is not invariant to these transformations, the generalization error of the invariant network will be better by a factor of square root T compared to the network which is not invariant. And we observed this also empirically. And we proposed a regularization technique that force features of points that we know that are invariant, of points that we want to be invariant to be the same. So if you want to be invariant to shifting, so you take the same image and shift it several times and force the network to get the same features for all the shifted versions of the same image. And with this regularization technique, we get better results than with no regularization or with other techniques that try to force invariance. Okay, so we are close to the end. I will just mention in 2 minutes these parts of how we may solve minimization problems by deep neural networks. And I will mention it very briefly. Consider this inverse problem where you have a measurement, you have a vector v, which is equal to unknown vector z times some linear operations plus noise. And then you can solve this problem using many techniques. One of the techniques for solving it is using L1 minimization or the lasso. So you want to find z, which is closest to v if you multiply it by a, with the L1 penalty. And then one of the techniques to solve this problem is using ISTA, the iterative shrinkage and thresholding algorithm, which take gradient step and then simple nonlinearity. It takes hundreds of iterations for this technique to converge. Jan LeCun and Gregor showed in 2010 that it's possible to learn the linear part of in the ISTA, and then you get much faster convergence. And it was not clear till recently why it is possible to do this thing. And this acceleration is not unique only to ISTA. It was used for many other inverse problems. It was used for Eulerian flow by Thomson, Schlatter, Sprechman, and Perlin, for binary samples by Remez et al., and so on and so forth. So basically what we showed in a recent work, we showed that it's possible to view the lista as a method that projects on a simpler set compared to a more complicated set in a way that you approximate the simpler set, if you have a more complicated set that you need a very complicated projection to use for it, and you have a simpler set that you have a simpler projection to project onto, if you will use the more complicated projection, you will be able to converge faster. The problem is that you don't know how to calculate this complicated projection, and then we show that if you use a linear mapping that is learned, you can have an inaccurate projection onto this set with a small error such that you get the faster convergence and the small error, and this gives you the faster convergence at the first iterations. I will not have time to go into the details. You can find, you will have the slides on the tutorial page, or you can see the paper on my website. And we also proposed an acceleration for lista. and I will summarize now. So the take-home message of the second part of the tutorial is that if you want to use, I believe that if you want to understand better deep learning, it is not enough just to look at the network structure. It is important also to look at the structure of the data. And in this way, you will be able to understand better what happened to distances throughout the network. You will be able to understand what happens to the data, and you will be able to understand better how to solve optimization problems with deep neural networks, and also the generalization error of the network. So thank you very much. These are the collaborators that worked with me on these works, and the slides appear on my website and also at the tutorial website. Thank you. So have now 10 minutes for questions, either to me or to Renee.
Hello, thank you very much for the tutorial. I have a question about the Gaussian width dimension or complexity. I forgot how it is called. Is it somehow related to the Minkowski dimension or the Hausdorff dimension, like which are used for fractals?
Yeah.
Measuring like
yeah. So it is related. So there are so you can have bounds between the two.
What sort of bounds?
So if I'm not wrong, the bound that you refer to is the same one like the Gaussian mean width, but with a variable that is on the sphere and not just random Gaussian variable. So I think it's related by square root 2 or something like that.
Okay. Okay, thank you.
I can point you later to the exact bound.
Okay, thanks.
So this Jacobian-based regularization, and actually the questions about the bound that you have in terms of the Jacobian, does this hold for a ReLU net? Because I mean, if you are very close to the boundary of a ReLU, the Jacobian, or the gradient on the zero side is 0 there, but you could actually have a very large gradient right across that decision boundary. So like in our paper that you mentioned with Joshua, we were looking at something more like an adversarial change, where you actually look at a finite but small perturbation and see how much the output changes based on that. And so like for ReLUs, this seems maybe more like what you want to look at.
So we tested the Jacobian with the ReLU, and it gave improvement. So
sorry, I was asking about like the bound that you have, so like the theory side of it.
Okay, so
like
again,
can you actually, does this bound actually hold for a ReLU network? Like
yeah. You just, what you need to have is just calculate the derivatives, and so 1 minute.
I guess what he's trying to say is that the Jacobian of what with respect to what, and if you have a ReLU, don't you get a discontinuity, and so the Jacobian can be infinity.
Okay, so what you can do, you can use a smoothened version of the ReLU. So in practice, use the ReLU. In the theory, use a smoothened version of the ReLU.
Okay, I see. I guess unless someone else has a question, I had another question about the first part, your part of the talk, where you had, actually I forget whose it was, but both the angle and the distance between points were decreasing. Okay, sorry. So I was wondering if you thought about or looked at like how those sort of interact. So like what would be interesting to me is if 2 points that start out, if there's 2 pairs of points such that the angle between one pair is larger than the angle between another pair, then as you apply like more and more layers, those points would be sort of pushed apart. The ones that had a larger angle at the beginning would be pushed apart faster, and so you could look at the limit of like the distance between those points as you add more layers. And so like that's what you would think would happen if the angles were constant, but then only the distance was being shrunk in a different way. So it's like 0.5 for the ones that were close and 0.7 for the ones that were far away. But since the angles are also getting pushed together, maybe there's some interaction so that they don't actually get like the ratio doesn't go to infinity.
Okay, so we checked for random networks how fast the angles shrink, and they don't shrink so fast. And we checked also how the distances behave, and we get things that are very similar to the factors that we got. So you get the factors that we have in our theorem based on the angles. But the really important thing that we wanted to get from our theorem is not just analyzing the behavior of the network with random Gaussian weights, which I think is nice theoretically, but the main thing that we wanted to understand is get some insight of what we get with training. So the insight that we got in this respect in training is that we think that you can view deeper network as more steps in gradient descent for learning the metric. That in one layer you are distorting distances in one direction, and then in the second layer you are distorting distances in another direction, and then the more complicated the data you have, the more layers you will need to make more distortions that at the end of the day will bring you to the shape that you want. So this is the insights that we got from why you need deeper things, not just to get stronger shrinkage, because if you just want to get stronger shrinkage in one direction, so it's easier to do it with one layer. So the reason that we believe that you need to get deeper is that we want to get shrinkage in different directions and in more complicated manners that you cannot get with just one layer.
Okay, thanks.
My question is to the first speaker. So you showed us how to construct matrices in the network so that the local minima would be global. But I think that after that, if you will do such things like batch normalization, dropout, the error will be less. And have you tried that? So after batch normalization, for example, it will not be convex, but still there is a, like, I think, boost in performance error.
So in principle, the use of batch normalization does not fall out of the framework as is, because batch normalization does not preserve the property of homogeneity, which is needed for the theorems. We are currently actively working on that topic and trying to study the effect of batch normalization. It seems as if the normalization sort of resets the degree of homogeneity. So instead of what I said, which is each layer adds an extra degree and you get degree k, each time you normalize, you reset it to 1 again. But we don't have the theorems for that case yet. So I agree with you that in practice, it seems to be the case that batch normalization works better. But as far as I know, there is currently no theory as to why this is the case. And I think the theory we have presented today can be extended, but we don't have it yet.
Okay, thank you.
Hi, thanks for the good talk. I have a question about the first part again, the very first part. That you had a very kind of practical result in terms of setting the matrix entries to 0 and growing the factorization. Yet when you do this in practice, probably we never check for exact zeros and we never reach that. And there is always this epsilon margin that we put on and kind of check whether that satisfies it. And if the kind of the framework is sensitive to that, then there will be no point in actually doing it. Did you do any experiments on how this works with different epsilons and that?
Great question. So that's all addressed in the details of the paper, but I didn't describe it. So two aspects of it. Aspect number one is that for matrix factorization in particular, and for the kind of norm that I had, sum of product of the norms, if the optimization algorithm that you happen to use is proximal gradient, then the proximal operator of that two norm is exactly the following. If the norm of the column is above a threshold, and the threshold is the lambda that multiplies the regularizer, then you shrink it by lambda. If it is below the threshold, you set it to 0. So the proximal operator sets things to 0 exactly to begin with, and everything that is below lambda. So from a practical perspective, for matrix factorization in that case is not a problem, if you use that algorithm. But you can tell me now, what if I choose to use gradient descent? So what would happen in that case is that the correct check is not to check for zeros, but rather to check for rank deficiency. You will get linearly dependent columns, which is equivalent, effectively.
Okay.
And so what we are doing really is solving for some coefficients that check rank deficiency and then convert it to the 0 case.
So we check the rank also, kind of.
Now, there is a step to go back. In fact, the very precise, purely coming out of the optimization way to check the condition is different. It's simply checking that the gradient of the loss dot product with a rank 1 factor is equal to the regularizer, which effectively it's super intuitive in the sense that says that you are at the global minimum where when the reduction you can make on the loss is compensated by the exact increase in the regularizer. Checking that condition is, has a name in optimization, is known as the polar problem. And checking the polar problem for simple cases is an eigenvalue problem. But that can be NP-hard in many cases. That's the NP-hard part that I was referring to. So in fact, checking, in some cases you can reduce it to check it, long story short, in some cases you can reduce it to check it for a 0. If you put the right algorithm, it's not a problem. But in the generic case, you need to check something more complex that involves solving an optimization problem of its own.
Okay, thanks. Great answer, actually.
A quick question to Rene. Do you have any feel regarding the dropout and whether there is any point looking at your future work that you're currently conducting? Is there any conditions in which we could go to extreme dropouts that far exceed 0.5, like 0.9 or 0.8 or even higher? Because in normal cases, it appears empirically that the convergence is very poor for very high dropouts.
Let me give you two answers, one practical and one more theoretical. The practical answer is we've been experimenting with this, and in fact, we just got the paper accepted to ICCV. What about using a variable dropout rate? What if your dropout rate is very low at the beginning, and then you keep increasing it and increasing it? The interpretation we have is it's like the way we learn, that we first learn with easy, but as time proceeds, we're giving harder and harder. And the pure experimental results show that increasing the rate gradually as you proceed in the iterations has improved performance with respect to choosing it to be fixed to be 0.5. But we don't have theory to justify and assess what happens. But my guess is simply that if you set it to be high from the very beginning, it's just not going to work, and you need to have it increase gradually. Interestingly, the theoretical answer that I gave earlier when someone asked me, is there any explanation for dropout? I said, yes, for matrix factorization, you put Bernoulli's, you take expectation, and it so happened that you get this exact regularizer that I was talking about, sum of products on norm, but squared. And I said, because of the squared, the theorems we had here fall apart. And to compensate for it, you need to vary the dropout rate. And you need to vary it in a way that it is larger for larger sizes. So the more complex the network, the more you have to drop out, kind of thing. I think that intuitive case, at least in the matrix factorization case, we have a very precise analysis of it. And it's very clear you need to increase it linearly with a number of neurons, effectively. So I think that it's opening an opportunity that there needs to be variations on dropout. First of all, I think in a year or two from now, I predict we'll have a good explanation for what dropout is doing. We'll understand the very precise regularization that is making, and we will understand, in fact, that it needs to be varied as you do the optimization. And how to vary it, it will be a function of the size of the network. That's my prediction, and I think we already have it wide for matrix factorization, but not for deep network yet.
Thank you. Great answer.
All right. So if there are no more questions, let me just announce that I've posted the slides for my part so far. To get to them from the website of CVPR, you just click on the website of the workshop and you will get directly there. Otherwise, you just go to my website, and in activities, I have all of the tutorials and workshops, and you will get it there. And right after, I'll post the slides from Raja. Okay? Thank you so much for coming and for staying this late.